So we'll just go ahead and take a look at this in case people want to tune in later. Or does anyone do that? Because one of the things that we do is if someone's missing, well then that's why we record this. Because we said if you're gone or absent, maybe check it into the Science Channel. See if there's anything there that can help you out to attain the missed content. Sorry about that. I had to take a quick break. So this problem, okay? Cattle gates. Does this look familiar? Didn't we solve a problem like this that had to deal with a pig? Okay. So in this case, oops. In cattle gates, they're designed to withstand 1,500 newtons. So when you see the label of newtons, what is that telling you? That's a force, okay? So this is what they're rated at, or this is what they're designed to withstand, okay? So that must mean you're making a comparison to that, okay? So is it going to be 1,501 newtons, 1,520 newtons, 10,000 newtons? We don't know, okay? So if an angry bull charges Mr. Wagner, again, this was from last year, he jumps over the cattle gate. Okay, so will this gate hold when we look at what's happening here? Okay, it says the bull has a mass of 1,100 kilograms. The bull moves to 1.4 meters per second squared to a top speed of 1,600 meters per second. And it looks like the R got erased over a time frame of 10 seconds. Will the gate hold? How fast was the animal moving when it started? Okay? So, two things that question is asking. What might be one question? Just tell me.
How much can the gate hold if it can hold the bull?
Well, is it going to hold? And then there's another part too to that question. What would that be?
How fast is the bull moving?
Yeah. When what? When it first started. So when we're talking about speed, when it first started, what does that possibly mean to you?
Velocity.
Can you be more specific though? Can you be more specific? Because it's not a final velocity if we're saying when it started.
Acceleration?
It's the initial velocity. Okay? So that was one question that we want to go over. And I think, yep, here we go. Here's another one that we want to go over. Well, that I want to go over with you to help you learn and understand what's on our science content standards. Not asking a whole lot. Would you agree? Okay. So the best way for us to help you is going through these together in class. And if you choose not to do that, that is a choice that you make. And it's just my opinion. It's not a very good one, but it's your choice. So in case we have problems reading that, it says, if a volleyball player has 13 kilograms per meter per second of motion placed into it, okay, we're talking about the ball then, okay, and the server had their hand moving at 17 meters per second, how much force was placed into the ball? That's one question. The time frame was 0.20 seconds, and the acceleration was 75 meters per second squared, okay? How fast was the arm moving at the lower end of the arc? And I think we would agree that if we're having problems working, if we can't solve these when we do these together, what's it going to be like when you're on your own? What would you think? Just guess.
Not very good.
Probably not very good. And people who choose, and again, it's a choice, who choose not to do this, what did we say the first week of school? What might be some reasons that maybe they're lazy
Don't want to do it.
and maybe don't want to do it, okay? And maybe they just don't care, and that's a choice. See, now we're talking about you volleyball players. Now that ball is gonna go up. You're gonna be thinking, so how fast was my arm moving at the bottom of this arc? We can pause this for a moment because we don't need to hear me ramble on. But okay, I think it's fair to say we can go back, and this is what we'll do. We'll have the problem up again. All right. All right. So we've read the problem. What is the next thing that we could or should probably do?
Figure out what we have.
Okay, so what do we know in this problem?
1,500 newtons.
Okay, so now it's fine when we write that. Okay, so I'm going to put it over here.
Anybody else got a clue on that?
Okay, and what else do we know? Just tell me.
The mass is 1,100 kilograms, and the acceleration is 1.4 meters per second squared.
Okay, and we'll stop there for just a moment. You're correct. You identified that as an acceleration. How did again, you're right. How did you know that though?
Because it's got meters per second squared.
It's got meters per second squared. So notice it doesn't say that it accelerated to 1.4. It's just going to say that it's moving, and because of that, that will then give you the proper amount of acceleration. Okay. So, is there anything else we know on the problem?
Velocity is 16 meters per second.
Okay, so velocity equals 16 meters per second. So, we may have to come back to that. And is there anything else we know on the problem? Okay,
And the velocity is actually the final velocity.
okay,
Because it,
you are correct. Okay, so, and when you came up with that presumption, how did you know that correctly though?
because it says to a top speed of 16 meters per second over a time frame of 10 seconds.
Okay,
And then the question said, how fast was the animal moving when it started?
so
Move where you can see.
when you have that,
You can't, it just follows you. I don't see anybody else having issues.
okay, so then you're correct because it says how much when it started. When you read that, that tells you that's got to be an initial velocity. So this was the goal, that we'd actually be able to write those down, and then we will do this. Okay? So now, what did the question ultimately ask? It wanted to know, will the gate hold, right? So how do we know? We don't know if that gate's going to hold. Because what is it rated to hold to? So this is what they're rated at, okay? So now this could be, is every cattle gate going to be rated that? I really don't know, but it's our way of using something like this because this is probably more of a practical application when you have guardrails over bridges, or what would you say, a cable system on the interstate that's going over bridges. It's unfortunate during the wintertime, people will run into those guardrails. They might lose control of their car. So those rails are designed then to withstand a certain amount of force. So it would be pretty important to be able to withstand maybe a large amount of force so that car doesn't end up in the ditch, because some of these ditches could be maybe 30 feet down, something like that. So this is trying to show you that there's practical applications for this. So what is it that we need to find then? We need to find the initial velocity. The question was, we can't put that tail on there. That's right. Okay. It's got to be an initial velocity we're looking for. And what else? Because we put it in a box. Right. So that must mean we need to find the force to see if it's, when it's rated at 1,500 newtons, will it hold? Okay. So in order to solve for force, there's three variables in that formula. Okay? Right. It's mass and acceleration. Okay? So then we're looking for the force, and we've got the mass, but we don't have an acceleration. So when it comes to three variables, you have to know two of them. But we've got a slight problem here. But what could we do you think?
The mass times the acceleration.
Okay? And then would that give us the force? Yeah. Sure. So one of the things we could do is take these times each other and find out, is it going to be above 1,500 newtons or is it going to be below 1,500 newtons? Okay? So then is this gate structurally sound then? No. So maybe it would be a good idea that engineers might need to, per se, redesign or strengthen their materials or their tensile strength. And I think there was a question, not question, but something similar when you're looking at that Eiffel Tower, okay? People might think that that was just an aesthetic look, but what is the reasoning for these cross beams in there?
If they let more force on one side, it'll...
Right. So what happens is if you only have one of these cross beams in here, okay, it's going to be able to only withstand half the load. In other words, if a wind force is coming in like this might bend and warp just a little bit. And if you have all of those doing in there, that's bad. Okay? But the designers and engineers said, well, let's put two cross beams in here. That way, no matter how much wind is coming in from either direction, it can withstand that force that's hitting that structure. Okay, so that answers that question. So this is a failure. We're just saying it's a failure. But we also want to know, well, how fast was that ball moving when it first started? So how could we solve that?
The acceleration.
Okay, so if we have an acceleration, which, okay, oops, we have an equal sign. What is on the left-hand side of that equation? 1.4, okay? What's on the right-hand side? We got a fraction.
VF minus VI.
Right, I mean, that's the formula, but 16, yes, okay? And then it's all over what? See? One of the things, notice we don't have this problem up here. But since we have all this in one place, we can refer back to this and say, okay, this is what we need to do. All right. So I would suggest let's get rid of that fraction. And what would we do? Okay? Just one side? Both sides. So what happens when you take 10 times 1.4? That gives you 14. You just have to move the decimal over one place. So now we've got rid of that fraction. What's left on top? And what we're illustrating is this. We've been doing this since week 1. Okay? Okay? So 16 minus the initial velocity. Okay? So what is it that we need to do to get rid of that 16 over here? You subtract that from both sides. What happens to these 16s then? They cancel out. We have negative VI equals negative 2. Well, we've got a problem here. Velocity can't be negative. But what happens if you have negatives on both sides? Yeah. You just multiply by -1 or divide. That makes them both positive. So approximately that bulb must have been moving at 2 meters per second. Then must have saw Mr. Wagner, went chasing after him. He jumps the gate to safety. But oh my, now that bulb plunges right into that gate, breaks it, cracks it right in half. Well, yeah, okay, so let's say there's a group of people, okay? So we're going to pick on Mr. Wagner. I'll let him know that we're picking on him earlier, or today. So if it's a group of you, you don't have to be the fastest person, right? Because if you're the fastest person, you're going to be fine. If you're not as fast as the fastest person, you might still be fine.
You just can't be last.
Right, you have to be faster than the slowest person. You just can't be last. So isn't that Ricky Bobby's problem too?
Yeah, first. If you're not first,
If you're not in first, you're last. Okay.
or grab a hot shot. That does not help you. So if my hot shot, you're gonna speed past that?
Yeah. No,
you're
you
not.
You be chasing me with that, you had me gone.
As we had said, the bowl was moving at 2 meters per second to start, and it was a failing structure. Okay. So now, problem number 2. You've read the problem. Front row, before we go, are we on the bus here? Second row, are we on the bus? Third row. So is that just, it's just sideways then? Is that correct? Okay. Back row? Okay. So here we have a separate problem. Okay. So we read this earlier. Okay. Next thing we should do is what? So what do we know?
Write down the information.
So
Know that we have 13 over 10y minus. What is that called? Oh. 13.
but it was stating, they're asking how fast was it moving at the lower end of the arc. So what type of variable might that, we know it's speed, we know it's meters per second, but what variable is it though? Well, it was at the lower, now you got to think about this, okay? So here's our yellow volleyball. So as this ball goes up, it's asking how fast was the arm moving at the lower end of the arc. We haven't made contact with it yet. So if we have a momentum, okay, what type of velocity is tied into momentum? It's mass, but what type of velocity? What type of velocity? What type of velocity? Oh, sorry, I'm thinking of what we're looking for. Whoever said 3 times in a row final was correct. My mistake, your fault. Okay, so this was a final velocity, which means we're looking for what instead? An initial velocity. Yes. Okay. So what is it that we need to solve for force? Okay, so what does force equal?
MA.
Right.
So
But what's our problem with that, though?
we don't have the math,
We don't have the mass.
and we can't, but we can use A and, no. We can use the A equals the
Okay.
BF minus the BI.
Okay, you're close. Okay. So what is it, since this is an initial velocity, this must be a final. Okay? So let's, because this was one of your equations, okay? We don't have an acceleration, we don't have a mass, okay? And we're looking for the force, okay? But what is it that these two variables have in common in their formula?
They have velocity.
They have what? What can you solve with those two variables? Sorry. We can find the mass from this. Because doesn't the product of a momentum equal the mass times the velocity? Do we have this velocity? Yes. It's right here. Okay? And we've got the product. Okay? So is there anything else that we could do? Yes, we can plug this in this formula and find what? We have the momentum. It's right here. Okay? So then, how do we find the mass from this? So who knows what to do next? Okay? Just if you know what to do, raise your hand and get them up high like this. Okay? So then this is your opportunity that if you don't know, you can interact and we can answer that. Okay? So how can we find the mass from this?
U times
Do we know the momentum?
Yes.
Okay, what is our momentum? 13. What is our velocity? Okay, so then what's left over in this equation here?
The kilograms and
M. We need to find the mass first. Okay? So how do we get M all by itself? You divide. Okay? So what is our mass now? What is 13 divided by 17? 0.76. That's kilograms. I don't know what the mass of the volleyball is. We'll just say that. Now you can look at it's probably printed on the volleyball. So I already know you're going to be curious that, okay, who can we pick on, you two? So all of a sudden you hear the whistle getting ready to serve, and here's this young lady. I know the mass is on here somewhere. So then you hear the official blow the whistle again. What happens if you hear the whistle twice? That's a good question. Yeah, they're saying serve the ball, but you're still trying to find the mass on that volleyball. Oh, well, you just say, hey, we got important things to look at. We need to see the mass of this volleyball. Okay. So we got our mass now. Can we find the force? Just tell me. Okay. What's your question?
13 divided by 17 and 17 divided by 30.
Okay. So you're going to divide that by 17. Okay. So now we have the mass. Do we have the acceleration? Do we have the acceleration in the back?
Yeah.
Can we find the force then?
Yeah.
Yes. So do we have enough information to solve for the initial velocity as well?
Yeah.
Yes. Okay? So, you tell me what to do.
0.76 times.
Well, what's on the left-hand side here?
Oh,
Or fraction.
No, not F.
Acceleration.
We're trying to solve for this variable.
Yeah, but wouldn't you need your acceleration?
Right. That's what I'm asking.
75.
75. Okay. What's on that we're not done yet, people. We're not done yet. Okay? So what's on the right-hand side of this equation then?
Fraction.
Okay, we got a fraction. And what's on top?
17.
Okay? What else?
20. 0.20.
Not 0.20.
Oh, your VI.
VI. And then what's on the bottom?
20. 0.20.
Okay? So how do we get rid of this fraction?
You just divide them.
No. You're going to multiply across.
Oh, yeah.
Okay?
17 VI.
So then, what is 0.2 times 75? It's what, 15 something?
Yeah.
Say that again? 15. Okay? So this 15 comes from taking 0.2 times 75. So we got to do the same thing over here. Oops. That's 20. These are canceled. So when we multiply that, that gives us 15. So what's left over on the right-hand side?
17 VI.
So how do we get VI all by itself?
17.
So what's our initial velocity? Because you get a negative number, but it just becomes positive because it's on both sides of the equation. So then what was our force then? Someone help me out. 57? So 57 newtons, that's how much force. Okay. So tomorrow we will, let's see here. We haven't formally assigned the vocabulary yet. We'll continue to talk about forces tomorrow, maybe some problem solving. How many are getting comfortable at solving these problems? So look at your classmates that have their hands up. If you are having problems, you can go to these classmates and ask for help. All right.
I have a question.
Yes.
It says exam.
Yeah, no, that was from last week. I just don't have it changed yet.
Oh,
All right. So we'll catch up to you next time.